This conference will now be recorded.
All right. Um, yeah, so hi, everyone who's watching this. My name is Nathan Van Dutschoten. I'm a member of the technical staff at CockroachDB. I've been here working on the team, working on the project for a little under 6 years, working on various aspects of performance, mostly around our transaction layer and then our replication layer below that. Um, I gave a talk about CockroachDB's use of clock synchronization a few weeks back, and unfortunately we had a little hiccup with the recording, and so this is a re-recording of that talk. Um, and yeah, back then we had some good questions, and so unfortunately we won't be able to record those. But we'll at least go through the content of this slide deck and discuss primarily the uses of clock synchronization within CockroachDB. So for this talk, here's the schedule. We're going to start with an introduction to Cockroach, because I know it may be new to some of the audience here. We'll then go into a discussion on the use of clocks and clock synchronization within Cockroach, and kind of the areas in which CockroachDB has always used clocks to power its transaction model. And then finally, we'll close with a discussion on some of the newer uses of clocks that push, or of clocks that are um, pushing the behavior of Cockroach further than it's gone before. And most of these are in the realm of multi-region transactions, where clocks synchronization can be even more helpful because of how high network latency gets when you're running in a global cluster. And so we'll start with a basic introduction to CockroachDB. I don't want to spend too much time here because there's plenty elsewhere on the web to find about this topic. But for those who are new, I think this will be helpful to set the stage. So CockroachDB is an open source distributed SQL database. What that means is it provides the ACID guarantees and the expressive interface of something like Postgres. And in fact, it speaks the exact same wire protocol as Postgres. And so when you're talking to Cockroach, your application actually thinks it's talking to Postgres. But it combines all of that with the scalability and the fault tolerance of a system like Cassandra, one of these resilient distributed systems. And so in combining those two qualities, it's sometimes classified as a new SQL system. Cockroach was originally inspired by Google Spanner, and I think that's a good place to start in this talk because I imagine that many in the clock community are familiar with Spanner. Uh, but for those who are unfamiliar, Spanner is well known for its use of atomic and GPS clocks, which is packaged into something it calls its True Time API. And it's well known because it uses clock synchronization in this large distributed system to provide very strong guarantees. And it was a really big step forward in demonstrating how clock synchronization could be used to power a very impressive distributed system. So I say it's a good place to start here, both because I think it's an area that people are familiar with, and it's an area that originally inspired Cockroach, um, but also one that is interesting to compare and contrast. Because Cockroach was inspired by Spanner, but it didn't have the ability to rely on such tightly synchronized clocks. Cockroach it's typically deployed on commodity hardware by enterprises or other application developers, or by Cockroach Labs, the company itself, in a managed service. Um, but it can't rely on having kind of the atomic and GPS clocks that Spanner does. And so this actually shaped some of the architecture of Cockroach, and it's one of the core reasons for some of the architectural differences between CockroachDB and Spanner. And so we'll start to see that as we go through these next few slides. So here's a quick introduction to Cockroach's architecture. Cockroach is a dynamically distributed transactional key value database with a SQL layer layered on top. So the system distributes data based on application patterns and data distribution accesses, and it then layers strongly consistent serializable transactions on top of a distributed key value store. In the parlance of the CAP theorem, Cockroach is a CP system, and so it's going to favor consistency over availability when that trade-off comes up. But in replicating and using quorum rights, it tries to provide availability whenever possible. And so data, as we'll see in a coming slide, it's replicated across multiple nodes in the system. So Cockroach is it's a shared nothing architecture, and that means that a series of homogeneous nodes come together, they combine to create this cluster, and that cluster then is exposed as a single logical database to an application. So any of these nodes can provide a gateway into this single logical database. You can add more nodes to the system, and that will scale out reads and also writes. Data will be spread out across these new nodes as they're added, and your storage and your transaction capacity will grow. You can actually scale this up across geographic regions or across clouds, and this can provide fault tolerance, and it can provide improvements to latency. And so we'll see that in a second. So in terms of fault tolerance, when you start spreading data across different failure domains, maybe these are just zones within a single cloud provider region, maybe these are actual cloud provider regions themselves, or as we saw in the previous slide, maybe these are even different clouds. All this means that you're more resilient to failures of individual failure domains. So in this example, we see that US East could go down, but if we're replicating across all three regions in the United States, then we're able to continue to provide full availability to this data. And similarly, replicating data across geographic boundaries also provides a strong benefit for latency. So we can place data close to users to provide faster latency to that data. It provides survivability, so we can survive in individual region failures. And it provides an ability to comply with newer and newer regulatory restrictions on where data can be placed. So to get to a discussion on clocks, I think we need to first touch briefly on the key value layer within CockroachDB. And this is to see where clocks actually aren't used in Cockroach. So below Cockroach's SQL layer is a monolithic key value layer. Each of these keys is organized in a sorted order, and the key space is it's spread out across nodes. So the key space is realized by dividing keys and their associated values up into contiguous 512 megabyte chunks. And we call these chunks ranges. So these ranges start empty. They grow as you add more data into them. They split when they get too large, and they merge with their neighbors when they fall back to and they get too small. Conceptually, a CockroachDB cluster starts with just a single range that's repeatedly split, rebalanced, merged, and spread around. In order to maintain the ordering between ranges, range indexing structure is added. So we store this indexing structure in a set of well-known ranges that are in a special part of the key space, known as the system key space. And so you can think of this kind of like a B tree, a distributed B tree. Now each of these ranges, each of these chunks of data is replicated. And Cockroach uses Raft for replication. Raft is a distributed consensus algorithm similar to Paxos. And what this means is that it actually is not using clocks in this step. There are no clocks at the Raft level. Raft will vote on changes as they come in, and if a majority of replicas vote on those changes, they will be accepted by the Raft group, and they will be applied to the applied state of this Raft group. There's no clock dependency at this level. Now, a distributed consensus algorithm provides a useful building block called atomic replication. Commands can be proposed by a leaseholder, so a distinguished member of this group. They're distributed to followers, and they're only accepted when a quorum of replicas have written the command to disk. In Raft, like I mentioned, a quorum means a strict majority. So let's say we have 3 replicas in a Raft group. A new write coming in will be distributed to all 3 replicas. And once 2 of those replicas have written the new write to disk, it will be considered accepted or committed. And that write will then be applied to the applied state. And so if the system crashes or restarts at any point after 2 replicas have written the command to their log, the write will still be present. So quorum replication is reasonable for writes because we are already going through the process of replicating those changes to all the replicas. But it's actually fairly burdensome for reads. Consider this example of reading a key Carl. Using a consensus read would involve talking to all 3 replicas. This means that our read would be limited to the network latency we see from a quorum of replicas. And we'd be writing a lot over the network. So that hurts. It would be really nice if we could read from a single replica and avoid the network round trip to the other replicas. Unfortunately, we can't just read from any replica because an arbitrary replica may be arbitrarily behind, which would cause stale reads. But the replica coordinating the writes, which we call the leaseholder, is always aware of the writes that have been committed. And so the leaseholder can serve as reads without communicating with other replicas. The leaseholder is said to hold the range lease. And these range leases give CockroachDB reads without consensus. The leaseholder also implements some of the concurrency control mechanisms used by transactions, such as key range locking. Now, the word lease may have tipped some of the audience off here. Now that we're using and we're allowing a single node to serve reads without consensus, we're approaching the use of clocks. And so, yeah, we've gotten to the place where Cockroach uses clocks, not at its replication layer, but the level above, at its distribution layer and at its transaction layer. And so it's really CockroachDB's transaction layer that has the most direct dependency on clocks. Within a range, Raft is used for coordination. But across ranges, transactions are used for coordination. And one thing to point out here is that CockroachDB uses multi-version concurrency control, or MVCC, within its transaction layer. And so that means that each key within the system has multiple versions, and these versions are all given a timestamp. And so using MVCC, transactions are able to ensure atomicity, because all of their writes and all of their reads will take place at the same timestamp. They're able to ensure serializability, which is really the highest level of isolation that transactions can have. And they're able to ensure consistency in the ACID sense of the term. And so, yeah, what do I mean by consistency here? I'm saying that the order of observed state changes is consistent with real time. Actually, in ACID, consistency means something a little bit different. But here, we're talking about concepts like linearizability. So when talking about consistency, the property that is often most used is called linearizability. And it's used to express the concept that if a transaction B causally follows a transaction A, meaning transaction A happened, it committed, and there's either a chance or it is the case that commit then led to transaction B beginning, then we want to say that transaction B will always observe transaction A's effects or its writes. And this is important because as an application developer, you wouldn't expect to perform an operation and then try to read that back and miss that operation. or you wouldn't expect to read a value and then try to read it again in a later transaction and then miss what you just read. All of these would be considered violations of consistency. And so in both CockroachDB and in Spanner, linearizability is really the focus. So the way this works in Cockroach is that when a transaction begins, it picks its local wall clock off whichever gateway it's operating on as its transaction timestamp. The thing to note here is there's not a central time oracle. There's no centralized place where all transaction timestamps are being pulled from. And this is important for high throughput and for multi-region deployments, because any centralized point in the system would become a central point of failure, and it would also impose latency if every transaction had to reach out to grab new timestamps. But if we're assigning timestamps from the local wall clock of each node in the system, then clock synchronization becomes a big problem, because if our clocks aren't synchronized well, what we could see is that you may get inversions in causality. You can imagine that a transaction hits node A and it writes at time 12, and then a causally dependent transaction hits node B, and because node B's clock is lagging node A's, it may actually get an earlier timestamp, maybe time 10. And what we don't want to happen is to have transaction B miss transaction A's write. So how does Spanner use true time to provide linearizability, given that there are still some inaccuracies between clocks? Well, it's actually surprisingly simple. Spanner waits on writes. It waits for some amount of time until it's sure that any future transaction will get a higher timestamp than any causal predecessor. And it's able to do this because Spanner's clocks are fairly well synchronized. They're synchronized to a degree where the offset between any two nodes is less than 7 milliseconds. That's what they cite in their original paper. It's actually, I've heard it's gotten a lot better since then in terms of their maximum offset bounds. And so if it only needs to wait for 7 milliseconds on writes, that's actually not that expensive, not much of a cost to pay in order to ensure that it provides this external consistency guarantee that it talks about. And so it's a pretty clever approach, and it really it demonstrates why their true time API is so important. Because you can imagine if true time was an order of magnitude worse at providing clock synchronization, these offsets would be 70 milliseconds, and this waiting on writes approach really wouldn't work anymore. 7 milliseconds is a reasonable price to pay on each write, but 70 milliseconds it's gets a little excessive. And so that's why CockroachDB can't really do the same thing as Spanner. It can't wait on writes because its expected clock offset bounds are just too large. Cockroach is run on commodity hardware with typically using NTP to synchronize these clocks, and so it can't expect to have such tight clock synchronization. And so waiting on writes would just be too long. So Cockroach needs to grapple with clock uncertainty between nodes a little more directly. It does so using what it calls a clock uncertainty interval. When a transaction begins, it picks both its commit or its transaction timestamp, and also establishes what it views as this uncertainty interval. This is its transaction timestamp, kind of an interval between its transaction timestamp and its transaction timestamp plus the maximum clock offset that the system believes any other node in the system could have. And so this is basically a way of saying this is an interval where causality is indeterminate. It's unclear if this transaction observes a write in this uncertainty interval, whether that write is actually in the transaction's causal future, whether it was concurrent with the transaction, or whether it was actually a predecessor of the transaction, and one that the transaction needs to observe to ensure causality. And so this quote sums up the difference in between CockroachDB and Spanner's approach fairly well. Um, while Spanner always waits after writes, so while each transaction, when it commits, waits for some single-digit number of milliseconds, CockroachDB sometimes retries transactions after reads. Um, and when I say sometimes, what I mean is that Cockroach won't do anything unless it observes an uncertain value in a transaction's uncertainty interval. And this means that if there's no contention in the workload, then there are never any retries. Um, but if a transaction does observe a potentially uncertain value in its uncertainty interval, it will try to change its commit timestamp to allow it to observe that uncertain value. And there are times when this leads to transaction retries. Um, the system never waits out the hundreds of millisecond clock offset bound, and so the the impact that clock synchronization has on latency is a little less direct, um, but the maximum clock offset can impact transaction throughput in that it can cause more or less transaction retries. So as a bit of a sidestep, it's useful to talk about the timestamp protocols that Cockroach is typically deployed alongside, um, because these are, to be honest, this isn't the most sophisticated part of CockroachDB. We rely on tools like NTPD or CronyD to synchronize clocks to a fairly conservative value of somewhere between 250 and 500 milliseconds, or at least that's what we then expect these protocols to provide in terms of clock synchronization. Um, and so we believe that this could be improved, but for now this is actually a static configuration where upon a process startup, it will configure its maximum offset that it expects to see between itself and any other process in a cluster of CockroachDB nodes. And by default, this is 500 milliseconds of clock skew. So there is some protection against clock skew in Cockroach. Um, between any two nodes, the system is running Marzullo's algorithm to detect the expected clock skew between those two nodes. And so it's monitoring how bad the skew is getting. And Cockroach will simply terminate any outlier nodes once they reach 80% of this maximum clock offset. And so this provides protection against clock skew getting bad enough to lead to some issues that we'll talk about on the next slide. But this still is it's somewhat blunt in that we are setting a static value and just testing against that value. There are also a few other protections where each host will monitor its own system clock, and if it ever detects jumps, sufficiently large jumps, it will also terminate itself. And processes will also prevent jumps across process restarts by periodically persisting their own wall clock. However, saying CockroachDB just uses NTP isn't quite accurate, because Cockroach actually uses a software level technique called hybrid logical clocks to improve some of its clock handling. Hybrid logical clocks provide timestamps that are a combination of physical and logical time. They kind of look like what we have here on the slide. The physical time is based on a node's coarsely synchronized system clock, and the logical time is based on Lamport's clocks. And so this has some distinct benefits over just using wall time to talk about time within the system. The first is that this can be used for causality tracking. Whenever a node sends an RPC to another node in the system, it attaches its local HLC clock, a timestamp from that clock, to the message. And when a node receives one of these messages, it updates its local clock. It kind of forwards its local clock to whatever timestamp was presented in the message. And so this can capture causal relationships between events on different nodes. And so this, if there is communication between events on different nodes, this HLC clock technique will keep nodes more tightly synchronized than just if we were using wall clocks alone. HLC clocks also provide strict monotonicity in that within and across restarts on a single node, a reading of the clock will always be monotonic. And this is important for a number of properties within the system. And finally, because nodes are forwarding their HLC timestamp upon the receipt of any new message for any other node in the system, there's this effect where, given a sufficient amount of inter-cluster communication, the HLC clocks within the system tend to converge and stabilize, again, even if their individual physical clocks have diverged. This doesn't provide a strong guarantee, but in practice, it can actually mask a number of clock synchronization errors. So when we're talking about clocks, it's useful within a distributed system to discuss what happens when clock expectations aren't held. What happens when a violation of clock synchronization is observed. So in Cockroach, because Raft has no clock dependency, data consistency between replicas is unaffected. So you'll never get in a split brain state or some case where data is corrupted. Similarly, because leaseholders are, because they're time-based, it may appear that leaseholders could allow for conflicting rights to ranges, but this isn't actually the case because leases within Cockroach, so within each range, their leaseholders are all disjoint in terms of the set of timestamps that they can act on. And so this is combined with a check after a Raft consensus round to reject rights initiated by older leases. And these together mean that nothing bad can happen with even if two nodes think they're a leaseholder at the same time. What can happen though under severe clock skew is that transactions can serve stale reads, and so this would violate single key linearizability. If transactions are if clocks are sufficiently skewed, then it's possible for a transaction to write some key value, and then for a later transaction to read below that key value without observing that first transaction in its uncertainty interval. And so this would violate linearizability. And so the interesting part to point out here is that isolation is preserved within CockroachDB regardless of clock skew. So Cockroach will remain serializable independent of clocks. However, Cockroach loses its linearizability behavior if clocks are sufficiently skewed. So to summarize, right off the bat, I think it's clear why Cockroach would be interested in better clocks. The tighter the clock offset bounds, the smaller these uncertainty intervals during transactions are. And so smaller uncertainty intervals mean that fewer transactions will restart, and under contention, transactions can have higher throughput. So in this case, clock synchronization doesn't directly impact latency like it does in Spanner, but it does indirectly through these transaction restarts. That said, what we're going to see next is an extension to CockroachDB's transaction model where clock synchronization and clock offset bounds does directly impact latency. The one other thing to point out here is that in both CockroachDB and in Spanner, it's actually the worst case clock offset that the system cares about, not the average case. The system wants to place guarantees based off of what it views as the worst case skew between any two nodes. And this is a theme within distributed systems where it's really the assumptions about the worst case that are more important. um, to the operation of those systems. So finally, onto the new addition in CockroachDB that I said actually pushes on clocks even further than we have before. So this new addition is called global tables, um, and global tables are a extension for multi-region deployments of CockroachDB. So deployments of CockroachDB that are run across the globe. Global tables are meant to provide low latency, strongly consistent reads on the same data from all regions in a global cluster. So to understand where this is coming from, let's talk about how geo-distributed systems usually treat data localization. So typically data is tagged with a location in a global cluster. In Cockroach, we call this homing. Data has a home. And this is important because it gives good performance to consistent access to that data in that data's home region. And so it works great for data with affinity to a specific region. We can see in this diagram here that the data is homed in the eastern side of the United States. Maybe this is user data for part of the Americas. And that user data will then it will primarily be accessed by those people in that geographic region. And so it makes sense to optimize the performance for that data. The data is still asynchronously replicated to other parts of the world to provide low latency stale reads. But strongly consistent access is restricted to access within the eastern United States here. So when if data's access patterns change, it makes sense to move the leader and the voting quorum to wherever we want to provide fast access, fast consistent access. So when we move the leader and the voting followers in this diagram, we then made it so that Europe could provide fast, consistent access to that data. But notice that, again, the data by default is still replicated everywhere. So anywhere in the globe can provide stale access to this data, but only the European nodes can provide fast, consistent access to that data. And typically, if operations are taking place that need consistent access, they'll actually have to hop over to Europe to make those changes. So I drew a distinction there between stale and non-stale reads. So to fully motivate global tables, I want to take a quick detour and talk about why stale reads are important and kind of what they are, how they work, but also why they can't be used in all situations. So a stale read is a historical read at some point in the past. And the idea here is that by reading in the past, Cockroach can serve the reads from follower replicas. It doesn't need to serve the read from the leaseholder replica. So let's see how this works. Each raft group in Cockroach maintains a piece of information called the closed timestamp. And the closed timestamp is a promise that no leader for that group will allow a write at an MVCC timestamp below what has already been closed. So here, for instance, this leader replica is closing timestamp 10. That means that it won't allow new writes below timestamp 10. So when a leader performs a write, it also attaches its current closed timestamp to that raft entry. And again, this write will go through raft, so it will get propagated to all of the other replicas in the system. And so then when a follower applies this entry, it can also bump their understanding of the closed timestamp to whatever was in the log entry. So during the write, the follower is also informed of the latest closed timestamp. And this lets followers know how stale a read has to be for them to be able to serve it instead of having to redirect it to the leaseholder. So we see here that if a write comes in after the closed timestamp, it will succeed, and future closed timestamps at higher timestamps will be propagated to followers. And once a follower has observed a closed timestamp, in this case it has observed 10, it's able to serve reads below time 10, with the guarantee that the leaseholder is never going to make any changes that invalidate this read. So there are two forms of stale reads, those with exact staleness and those with bounded staleness. This distinction relates to who chooses how far in the past to run the reads. The distinction here isn't super important for this talk. The one thing to take away is just either way, stale reads often come with a large latency benefit because they can be served without cross-region communication. They can be served from the local replica, regardless of whether that replica is the leader or a voting follower or a non-voting follower. But these stale reads also come with a major limitation, in that they can only be run from read-only transactions. Because these transactions need to be okay with observing stale state in the system. So any transaction that writes will need all of its reads to be strongly consistent. A read-write transaction simply can't use follower reads. Or we get ourselves in all kinds of trouble with ACID. And so while stale reads can provide a large latency benefit, they really can't be used in all cases. So back to global tables, which is where the new introduction of clocks is being used. Global tables provide strongly consistent low latency reads from all regions. So they provide strongly consistent follower reads. In other words, reads from any replica, not just the leaseholder. And this means that these reads can be used in read-write transactions, run from any region, and they'll always get low latency. The trade-off here is that write latency to these tables is penalized to provide these properties. Now, to make this all possible, we had to add a significant extension to our transaction model called non-blocking transactions. And this is where the new introduction of clocks is takes. This is where the clocks are being used more. Now, I said that the motivating use case here was for data that is not localized to a single region. So data where the same piece of information is read often from all regions. So there's not a natural home for that data's leaseholder. The canonical example here is a reference table or a dimension table, or some type of table that localized data may reference, maybe through a foreign key, but that isn't localized itself. So we can see such a setup in this schema here. We would expect for a customer and their orders to have strong access locality to wherever that customer resides. However, the products table that a customer is ordering from won't have strong access locality. A customer in a completely different region will reference the same set of products when placing an order. Now, the reason why the parent table of a foreign key relationship makes for an interesting example here is because the parent is read during a foreign key check, by definition in a read-write transaction. So, for instance, when a user runs this insert statement, the database is going to perform a foreign key lookup on the products table and the customers table in the same serializable transaction. And these lookups need to be strongly consistent. Now, the customer's lookup will likely be fast because it will be homed in the same region as the new order. But since there's not a natural home for rows in the products table, there's not a good place to home these rows. Luckily, global tables can save us. As long as we're okay with slightly slower writes to the products table, we can make the table fast for reads from all regions consistently. And so no matter where this insert statement is being run from, we'll expect single-digit millisecond latency. So let's see how global tables are implemented under the hood. Perhaps the most straightforward way they could have been implemented is by forcing writes to the table to synchronously write to every replica before committing. So instead of performing quorum writes, we would have a write everywhere, read anywhere replication scheme. Now this works, and yet it has a glaring issue, which is that the failure of any single replica would kill write availability. And so we'd no longer be fault tolerant, which is mostly a showstopper. Okay, so what about another approach? If we can't tolerate the availability loss of synchronously broadcasting, and we want to keep quorum writes, but we also don't want to visit the leader on every read, then maybe we can do what some other systems do and perform quorum reads. Instead of reading from the leader, we can read from the closest majority of replicas to determine which value to read. This trades marginally better latency in cases where the leader is far away for more work on each read. And it also doesn't even eliminate wide area network communication during reads, because even these closer replicas may still be across a WAN hop. So it doesn't really get us what we want either. So maybe we go back to the initial scheme of broadcasting writes to all replicas, but try to claw back some fault tolerance. The problem was that once a follower disappeared, maybe it crashed or maybe it was just partitioned, we had no way to stop it from serving reads that could invalidate future writes. And so we had no way to safely perform new writes. So maybe we give every replica a read lease, and we periodically extend them. And so a partition follower can only serve reads up to some maximum MVCC timestamp. This means that if a replica disappears, we're only unavailable to serve writes for some limited period of time, really until this lease expires. And eventually we will get to write again. So we've gotten back some fault tolerance by using a scheme similar to the idea of a quorum lease. And this works. We trade slower write latency for low read latency, and we still ensure high availability. So when designing global tables, we started down this path, but something didn't really feel right. For starters, this was seriously complex to design because there's a lot of state being maintained here. But more than that, we started thinking about low latency reads, not just in terms of their average latency, but in terms of their tail latency. And the thing we noticed was that read-write contention on these tables would lead to significant latency spikes due to reads blocking on in-flight writes. You can imagine that from the perspective of a read, a consensus write is acquiring a distributed lock. The write is broadcast to all replicas across the globe, and each replica will check whether any previous read has invalidated that proposed write. If the write is invalid, the follower will send back a rejection. But if the write is still valid, the follower will acquire a lock and acknowledge the write. At this point, that lock needs to start blocking conflicting reads, because these reads don't know whether to serve the old value or the new value. It depends on whether this write is eventually going to succeed or not. Now these ACKs travel back to the leader, and if all replicas acknowledge the write, then the follower is told to apply the write and release its locks. But that's a lock held for at least one global round trip of communication that's blocking what is meant to be low latency reads. And things actually get a little worse than this, because we don't want reads to be able to starve out writes. So we may need to introduce an initial round of communication to acquire locks earlier and determine what timestamp to even write at. Or we can do this optimistically, in which case we would fall back to 2 rounds of global communication only when there is read-write contention. Now there are various analogies we can make here to consensus protocols like single decree Paxos or fast Paxos. And it's interesting to do so. But the point I'm really trying to make here is that Paxos implies blocking on communication. And communication isn't cheap when run across the globe. We're talking about a read that normally takes a few milliseconds, suddenly taking 1 or 2 or even 300 milliseconds when waiting on a contending write. So we asked ourselves, how could we avoid this problem? How could we coordinate between reads and writes without blocking on communication? And this led us to a realization. The idea is that we could use clocks and not locks to coordinate, just like Cockroach does in other areas of the system. Now, a reminder, Cockroach doesn't use sophisticated GPS or atomic clocks, at least by default, like Spanner does. And yet, using its hybrid logical clock scheme, it is fairly easy to get reliable clock synchronization down well below the 300 milliseconds or so we saw in the previous example. And with a little effort using just software, we can actually drive this clock sync down much further. And of course, using hardware like the TAP project is exploring, we could drive this down much, much further. And so we explored ways that we could use coarsely synchronized clocks to coordinate between these reads and writes. And this would allow us to move communication about these writes outside of the read-write conflict boundaries to prevent these writes from blocking reads. And this actually turned out to be a natural extension of what the system was already doing. The key idea here is that we push the timestamp of writes on these tables into the future. And we also push the publication of close timestamp notifications into the future. Remember that these are the notifications that a leader sends to its followers to tell them how far in the past they're allowed to read. Only here, these notifications carry timestamps in the future. So followers can serve reads at the present time with no staleness. And when we say serving reads at the present time, what we mean is consistent reads, strongly consistent reads. So by shifting writes into the future, we actually get non-stale reads from all replicas. The way to think about this is that we're scheduling writes into the future and then using clocks to coordinate visibility and not using locks to do so. Now, if there is no contention between reads and writes, this all works beautifully, but that's not really saying much. If there is contention, how do we ensure consistency? In other words, how do we ensure the properties of read writes and monotonic reads? These are two properties that combine to give us linearizability in this case. Now, read writes means that once a write completes, any future read will observe the effect of that write. And monotonic reads means that once a read completes, any future read will observe the same or later value. And here's where the clocks come into play. To ensure read writes, we introduced a concept called commit wait into CockroachDB. Commit wait is a delay that writes will perform after committing, before acknowledging the commit. Now, this may sound very familiar. That's because the name is coming from Spanner. This is a variation on what Google Spanner does to ensure external consistency. Although this is a little different, and the details there are subtle, but in Cockroach, this is a wait paid after a transaction removes its locks, and not before. This is also a cost that Cockroach only pays when writing to global tables. And it's actually why writes to global tables are slower. These were waiting out the maximum clock offset between any nodes within the system. Now, to ensure monotonic reads, we extend the read uncertainty interval concept that we talked about before. Remember that a read's uncertainty interval is an interval above its read timestamp, equal in size to the maximum clock offset between any two nodes. And if a read observes a write in that uncertainty interval, it usually bumps its read timestamp above the write and immediately retries. Turns out that it's able to do this because it knows that those writes have a valid clock timestamp. And so it can immediately retry at the higher timestamp, which it knows is a real timestamp. However, if it observes a write in its uncertainty interval in a global table, it may actually be seeing timestamps from the future. We call these synthetic timestamps. And so it can't just immediately bump its timestamp to that higher timestamp and retry. Instead, it bumps its read timestamp to that higher timestamp and then waits until that timestamp, which would be in the future, is below its present time based off its local wall clock. So this means that the maximum time that a read will ever have to wait to coordinate with a write is equal to the clock synchronization offset. Now this is a major improvement because not only is this less than global communication latency, but it's also something we can continue to drive down. We're not limited by the speed of light here. And we can use various techniques within CockroachDB and within environments running CockroachDB to improve clock synchronization. Again, if we're assuming a reliance on clock synchronization, we do need to have a discussion about what happens if clock sync bounds are violated. Now, assuming a maximum rate of clock drift, Cockroach can do everything in its power to shut things down before a clock gets too out of sync. But that's not really a complete answer. The full answer is that if clock skew is not properly detected in time, this can result in stale reads. Now, this is transient in that the data won't be corrupted, but clients could still observe violations of causal order between two transactions. But this is actually a hazard that already existed. We talked about it before. So this new use of clocks isn't introducing any new concerns. And again, a subtle point here is that sufficiently skewed clocks can result in violations of linearizability, but not in violations of serializability. In other words, causality is enforced through clocks, but isolation is not. So we see that using semi-synchronized clocks and this extension to our transaction model, we've managed to drive down the latency on reads on these global tables, offering optimal latency in the case of uncorrelated reads, and offering reliable tail latency that we can improve upon by improving clock synchronization. This is all possible because we move communication outside of these read-write conflict boundaries on these global tables. So again, global tables maximize write latency to optimize read latency. This means that they're not a perfect fit in all cases, but they're an extremely important part of the puzzle for read-heavy data that does not have strong access locality. So let's recap. Would better clock sync help CockroachDB? Well, the answer is absolutely. Cockroach relies on clocks, and the tighter the clock synchronization, the better CockroachDB is to run. The long answer is that things are a little more subtle. Better clock synchronization would lead to a few major improvements. The first is fewer transaction retries. In base CockroachDB, and especially when running CockroachDB in only a single region or only a small set of regions, you typically won't use global tables. And so the big area that better clocks would help is that they would lead to smaller read uncertainty intervals for transactions. Smaller read uncertainty intervals mean higher throughput under read-write contention. These fewer transactions would retry. In global clusters, though, things get even better with improved clocks. This means lower write latency to global tables and lower read latency to global tables that hit contention. So while clock synchronization indirectly impacts performance for single region clusters, it directly impacts performance for multi-region clusters. Tighter clock synchronization would also help in that it could allow Cockroach to provide strict serializability, which means external consistency even for unrelated transactions, those whose causal order can't be detected through the read uncertainty interval concept. And so in the real presentation of this with an audience, we spent some time talking about some of the questions that CockroachDB had as well for this group, OCP TAP. Right now, there's not really an audience, so I think this is my last slide. I'm going to then hop back here because I think this is probably the most important slide, and I'm going to close out with that. And so thank you for listening to this talk. It was a real pleasure being able to talk to the OCP TAP community, and I hope we continue to interact going forward. So thank you.